Okay, so let's look at another example. This time I will not imagine a single infinite wire, but rather two parallel plates. I'm just looking from the sides. I have these two infinite plates. And let's say one of them has a surface charge density sigma plus sigma, and the other one has a surface charge density minus sigma. What is the electric field at everywhere? Now we will look at three regions. This is region 1, region 2, and region 3. So let's calculate the electric fields. We already know that the electric field from our previous examples of an infinite plane, if this is our infinite plane, the electric field at everywhere is sigma over 2 epsilon 0. And if assuming sigma is positive, it's always pointing away from the plate. At this point, the electric field will be pointing upwards, again, assuming sigma is positive. And at this point, the electric field will be pointing downwards. Now let's look at this point, a point over here. Yes? Now, up to this point, we have been always using the superposition principle. So if you can divide your charges into various sets of charges and calculate the electric field of each one of these sets, you just add them up. So here I have one set of charges. They will be creating their electric field at that point. Let's call that E plus. What will be the direction of the electric field created by this field, by this plate? Towards the left. This is E plus. What about the electric field created by the negative charges at that point? It will be towards the right. What is the magnitude of E plus? Less than E minus. Equal or less than or greater than. So which one is larger, the electric field created by this one or this one in magnitude? First one.
Because we are talking about infinite planes, so we say that sigma over 2 epsilon. So then say it's out of the region, so it's 0. So they are equal. Then we sum up, it's 0.
So your friend says that their magnitude should be equal. Yep, they're infinite planes. So that's why, although that point is closer to this plane than this one, since at least in this problem we are assuming they are infinitely large, so it doesn't matter at which distance you are, so their magnitudes will be equal. The magnitude of E plus will be equal to the magnitude of E minus, which is given by sigma over 2 epsilon 0. So I have two vectors of equal magnitude pointing in opposite direction. The total electric field will be 0. Everywhere in region 1. Now let's pick up a point somewhere over here. Again, the positive plate will create an electric field. The negative plate will create an electric field. What is the direction of the electric field created by the positive plate? Okay, in that direction. What about the electric field created by the negative plate? Well, towards the plate. What about their magnitudes? Which one is larger? They will be equal. It doesn't matter which side of the plate we are. The electric field created by the plate always has the same magnitude independent of its position. Again, both of these magnitudes will be just sigma over 2 epsilon 0. So the electric field in this region will also be 0. Now let's pick up a point, some random point in between the plates. Well, what will be the direction of the electric field created by the positive plate? It will be towards the right. What is the direction of the electric field created by the negatively charged plate? It will be also towards the right. So this only in between, they will not cancel. So we will have a total electric field in region 2. Well, each one of them has the magnitude sigma over 2 epsilon 0. When we sum them up, it's just sigma over epsilon 0. This is the magnitude of the total electric field. Let's call the horizontal direction the x direction, so it will be in the I direction. So essentially, if you have two infinitely parallel plates, the electric field is 0 almost everywhere, except then the region in between. And in between, you have the electric field, which is constant throughout this volume. It's the same whether you are at this point, at this point, at that point. Okay, when was the last time any one of you had seen an infinite plate? They basically do not exist. So these results are approximate. Now let's look at how approximate they are. This can be a model to check how approximate, how well they work. So we had this disk. We had this finite disk. And we were at a distance L from the disk at a radius R from the disk. Do you know Taylor? You probably remember Taylor expansion. You have seen Taylor expansion, right? Well, let me give you an approximation. If you have 1 plus x squared, you can make its expansion, right? This is 1 plus 2x plus x squared. What about 1 plus x to the power cubed? This is 1 plus 3x squared plus 3x plus x. Now this is 3x. 3x squared plus x cubed. In fact, 1 plus x to the power n, you see here there is a 2, which is the same power. Here there is a 3, which is the same power. So 1 plus x to the power n is 1 plus n times x plus all the other terms. Now let's just imagine x is something like 10 to the power minus 10. If this is 10 to the power minus 10, well, it is much small, very small compared to this one. But this term is even smaller than this one. So if x is very small, I can just ignore these terms. They are very small. Just throw them away. So this term will be the first correction to 1. If x is very small, this term will be very close to 1, and this is the first correction. And in fact, although in these two examples you have integer powers, this is true for any power. Whatever the value of n is, this expansion is always true. Whether n is a real number, positive number, negative number, complex number, this is always true. Anyway, probably this semester you will see that in Calculus 2. Well, let's see. in this problem, do I have something small? Well, if I have a very large disk, then R will be large, L will be small, so L over R will be small. So let me just rewrite this as E is equal to sigma over 2 epsilon 0 I 1 minus 1 over R over L multiplied by 1 plus L over R squared under the square root. This is equal to sigma over 2 epsilon 0 I 1 minus L over R times 1 plus L over R squared to the power minus 1/2. Sigma over 2 epsilon 0 I 1 minus L over R, well, approximately just this one. This just approximately. Well, can I ignore this? What I did was, this is L over R is already much smaller than 1. I am already multiplying that with something very small. So any corrections to this, due to this term, will be just a small number multiplied by a small number. I can just ignore it. So when do I have the infinite plane result? If I can ignore this term, the electric field created by the disk is equal to the electric field created by an infinite plate. So if L is the distance from the disk. Look over there. L is the distance from the disk. If L is very small compared to the size of the disk, I can just ignore this term, and the total electric field will be equal to the electric field created by an infinite plate. So this infinite plate example is an approximation that is valid if you have the size of the system, which is given by R, determined by R, and then you have the distance of the point of interest from the disk. And it will also be relevant from the edges. If you are away from the edges, and if you are very close to the disk, your result will be almost exact. So in a real-life example, if you have a very large plate, not an infinite one, what you will have is the electric field over here will be the electric field of an infinite plate. The electric field over here will also be an electric field of an infinite plate. Similarly over here. But if you come close to the edges, the electric field will no longer be the electric field of an infinite plate. It will be somewhere in this direction. But as long as you are away from the edges and very close to the surface, you can approximate it by an infinite plate. And in fact, one of the places where this approximation works quite well is the capacitors. You have probably seen capacitors, right? So they are basically two conducting plates placed very close to each other. In general, you just put some very thin dielectric in between the plates. So just imagine taking 1 centimeter squared conductors separated by less than 1 millimeter. Well, as long as you are not close to the edges, you can just approximate it by an infinite plate, and this approximation works quite well. Any questions? So we have the electric fields. And well, the electric fields exert forces on charges. And if you have forces acting on charges, then you can use all the Newton's dynamics that you have learned last year. So let's see how these will behave. Motion of charges in uniform electric field. Now, one example you can think of is, let's say you have an infinite plate or approximately infinite plate. And now you have another one. But this other one might have a hole in it. And suppose you exert some charges. You put some charges on these plates, plus sigma, minus sigma. Well, our previous results hold for infinite plates without any holes. But they will still give a good approximation as long as this hole is also very small. So in that limit, inside we know that there is an electric field at every point. The electric field is pointing in this direction, and it has a magnitude given by sigma over epsilon 0. Now let's imagine you put some charge over here with mass m. Well, then the force acting on that charge will be just q times E, and it will have a magnitude given by q sigma epsilon over epsilon 0. Well, Newton tells us that the acceleration of an object is equal to the force of the object divided by its mass. So this is q over m. Let me write sigma over epsilon 0 in the horizontal direction. Let me just call that direction I, the unit I hat. So this is the force, the acceleration acting on an object. So it's doing a motion with constant acceleration. And then you can just pick up all the results that you have learned last semester. So its velocity as a function of time will be its initial velocity plus acceleration times t, which is its initial velocity plus q over m sigma over epsilon 0 times t in the horizontal direction. And its position as a function of time will be just its initial position plus its initial speed multiplied by the time plus 1 over 2 its acceleration times t squared. In fact, this is one of the mechanisms where you can create electron beams. So you can just put some source of electrons over here, put put some charges on these plates and cause the electrons to accelerate, and then through this hole they will get out. You accelerate them, and once they leave this hole with some speed v, there's no electric field outside, so they will just keep moving. This is at least one way of creating some electron accelerators. And then with those electron beams, you can do whatever you like. For example, you can treat different materials. One of the examples is you probably have seen these wraps around. Sometimes you have these wraps with many water bottles. They stretch. Do you realize what I'm talking about? So you have these bottles. This box of bottles. And they are wrapped on plastic, and this plastic kind of tightly wraps around them. So this tight wrapping can be created by bombarding this plastic with electrons. So if you bombard them with electrons, and then they are compressed. Also, certain tires are treated with electron beams. So the tires are just polymers, and if you just send electrons through this polymer, what it does is it just creates various bonds in the polymer, additional bonds, and that makes the polymer stronger. Now, another possible motion would be, well, instead of sending it horizontally in this vertical to the plates, you can just send it horizontally. Well, essentially, it's exactly the same problem. It's plus sigma, minus sigma. You send it through this parallel plates. In this case, the only difference from this problem is that in this problem, the electric field is in the direction of the initial velocity. You set the initial point to 0. The v0 is in the direction of t, so the trajectory of the object is just a straight line. In this problem, the initial velocity, this is v0, is perpendicular to the electric field. The electric field is pointing downward, so it's a motion with constant acceleration, constant vertical acceleration, where the initial motion is horizontally. This problem is essentially identically the same problem with motion under constant gravitational acceleration. There is a vertical force, so the trajectory is essentially a parabola. Now, later on, when we study the magnetic field, the force acting on the charges due to the magnetic field, we will see that we can arrange the electric and the magnetic fields such that only electrons having a given velocity will be able to go through. And all the other electrons will either hit the lower plate or the upper plate. So that way you have a set of electrons, because the problem is usually the initially created electrons, they don't have a definite energy, a definite speed. They have various energies pointing in different speeds pointing in different directions. And you would like to pick one of them, electrons of given energy. That using this electric and magnetic field in combination, you can do such a filter. Well, this will be more relevant for materials. You see, at the end of the day, if you look at any material, it's made up of atoms and molecules. And the molecules, they are not always neutral throughout the molecule. If you look at the water molecule, for example, it has an oxygen atom and 2 hydrogen atoms attached to it. As a whole, the molecule is neutral. But if you look at locally, the hydrogen atoms are slightly positively charged, whereas the oxygen atom is slightly negatively charged. In fact, due to these positive and negative charges, the water molecules can form very small, very weak bonds called the hydrogen bonds. And in fact, it's one of most of the properties of the water molecule is determined by these positive and negative charges. So you see, this is a simple system where although the system as a whole is neutral, the positive and negative charges are not at the same point. There is no uniform surface charge density. The charge density is not uniform. Some regions are slightly positive, some other regions are slightly negative. Now, one model we had already studied for such systems is, for example, we looked at this problem. We looked at some positive charge over here and a negative charge somewhere else. And then we calculated the electric field of this system along this central line. Let's say at this point, this positive charge created an electric field in this direction, and this negative charge created an electric field in this direction. And when you sum them up, You can consider summing them up vectorially. This is the resultant electric field. At least at that point, it was horizontal. The vertical components, they just canceled each other. And, well, let's calculate the total electric field. Well, this positive charge at this point will create an electric field with magnitude 1 over 4 pi epsilon 0. Let me call this separation d. And let me also call this length L in this case. Well, this distance squared is just L squared plus d over 2 squared under the square root. And the charge creating the electric field, no, there is no square root, sorry. So 1 over 4 pi epsilon 0 is from Coulomb's law. Q is the charge creating the electric field. L squared plus d over 2 squared is the distance squared of this point from this charge. Then to calculate the horizontal component, I have to multiply with the cosine of that angle, theta. This is theta. This is theta. This is theta. This is theta. And cosine of theta is d over 2 divided by L squared plus d over 2 squared under the square root. D over 2 is this length, and this square root is this hypotenuse. So cosine of this angle is just the adjacent side divided by the hypotenuse. So that is the magnitude of the electric field created by this plus Q charge. If I multiply by cosine theta, it's d over 2 divided by L squared plus d over 2 squared. So that is the horizontal component of the electric field created by the positive charge. Then I have the negative charge, which is creating an electric field of exactly equal magnitude, but pointing in this direction. But its horizontal component, since it also makes the same angle, theta, the horizontal component is also exactly the same as the horizontal component of this one. So I just multiply it by 2 in the horizontal direction. That is the electric field created by this dipole at this point. So these two cancel, and I end up having 1 over 4 pi epsilon 0 q times d times I hat divided by L squared plus d over 2 squared to the power 3 halves. Now this Q times D has a special name. You see, Q is the charges, well, the charge of any one of them, the magnitude of the charge of any one of them. D is the distance between the charges. This is called the electric dipole moment. In fact, that is also a vector on its own. So this is the magnitude of the electric dipole moment. The direction is pointing from the negative charge towards the positive charge. So the electric dipole moment vector is defined as Q times D in the minus I hat direction. Well, minus I hat because I happen to define the I hat vector to be from the positive charge to the negative charge. So this is just a vector pointing from the negative charge to the positive charge. That is the definition of the electric dipole moment vector. Now, if I put an electric dipole in a uniform electric field, what will be the force that the dipole will feel? Suppose I have a dipole. This is minus q, this is plus q, this is the electric dipole vector. I put it in some uniform electric field, meaning that the electric field is the same everywhere. What will be the force it will feel? Well, let's see. The force that a system feels will be the force acting on its various parts. You just sum the forces. Well, if there is an electric field in this region, the plus q charge will feel a force given by plus q times E. This is the electric field, electric force acting on a charge q by the electric field E. Right? Plus, then what will be the force that this minus q charge feels in an electric field? Minus q times the electric field. Let me put a plus and a minus over there, meaning that this is the electric field at the position of the plus charge. This is the electric field at the position of the minus charge. So if electric field is uniform, uniform means that it doesn't change from point to point. So E plus will be equal to E minus. So the total force that the dipole feels will be q times E plus minus E minus, which is just 0. So the dipole doesn't feel any force in an electric field, in a uniform electric field. So if you put these water molecules in a uniform electric field, well, you say uniform doesn't necessarily mean that it is uniform everywhere. The water molecule is very small. As long as the electric field doesn't change within the volume of the water molecule, well, the water molecule will not feel any force due to this charge, due to this electric field. What else does the forces do? If you have studied the effects of forces, one thing is it can cause acceleration. And what else can a force do? Especially when the forces are acting on an extended object. Change the object's shape, but let's look at rigid objects. Its shape doesn't change. In a sense, rotate the object. So the analog of force for rotations, do you remember? The torque. So you see, if I put an electric field, if I put this dipole in an electric field, let's assume that the electric field is always pointing in this direction. And my dipole is pointing in that direction. Well, this plus q charge will feel a force in this direction, in the direction of the electric field. The minus q charge will feel a force in the direction opposite to the electric field. And if the electric field is uniform, the magnitudes of these two forces will be the same. They are pointing in opposite directions. That is why we have the total force equal to 0. But you see, they are not acting at the same point, which essentially means that they can create a torque. It will cause the dipole to rotate. Now let's calculate the torque acting on this dipole due to these forces. Let me just draw it a bit larger. So this is the plus q. This is the minus q charge. The electric field is uniform everywhere in this direction. let us assume that this dipole cannot change its shape. Well, to change the shape of the water molecule, you need a really strong electric field. Let's say you don't have such strong electric field, but mild electric fields. But still, it can change the orientation of the molecule, or in this case, the dipole. Well, the force will be pointing in this direction for the plus charge, and it will be pointing in this direction for the minus charge. So how do you calculate the torque? Do you remember the vectorial form of torque? The torque is the vectorial product of R and F. R is the position vector of the point that the force is acting on. But of course, if you want to talk about the R, you have to choose an origin. Which origin would you like to choose? The center. Well, you can choose whichever point you like, but the center is a reasonable choice, let's say. Now, what is the direction of R cross F plus? So the total torque for my system will be R plus cross F plus. The force acting on the positive charge, and this is the position of the positive charge, plus R minus cross F minus. Again, the force acting on the negative charge, and this is the position of the negative charge where the force is acting. So what is the direction of R cross F? R cross F into the R plus cross F plus. This is into the screen. What about this one? R minus cross F minus. What is the direction of this one? The same. This is the R cross vector. F minus is in that direction. This is the direction of the cross product. Let's write the magnitude. What is the magnitude of R cross F? R plus cross F plus. Let me also define some angles. Let me call this angle theta. So what is the magnitude of R plus cross F minus? How do you calculate the magnitude of the cross product of two vectors? Multiply the magnitudes. R plus has this magnitude, which is d over 2. F minus has the magnitude of q times E. And also, this is the product of the magnitudes. And what else?
The force needs to be perpendicular to that.
Either you take the component of the force perpendicular to this line, or you just multiply by this sine of theta. They are the same thing. This is the torque created by the force acting on the positive charge. Well, this is the same thing. The force acting on the negative charge has the same magnitude, R minus being this distance, and this distance is equal to that distance. So R minus and R plus, they have the same magnitude. And the angle between R minus and F minus is also the same. So it's just the same. This is the total torque. So the torque has a magnitude Q times D times E times sine theta. And you see, again, we have that same combination, Q times D, which is just P times E times sine theta. So torque, being a vector, its magnitude is exactly the same as P cross E. You see, P vector is this one. This is the P vector. So the magnitude of P cross E would be the magnitude of P multiplied by magnitude of E, which is this one, multiplied by the angle between the two. Well, you see the electric field is pointing in this direction. P is pointing in that direction. The angle between the two is theta. So here we have P cross E has the same magnitude as the torque. Well, what about the direction of P cross E? You see, P is in that direction, E is in that direction. P cross E is into the screen. But we already said that the torque is also into the screen. So here we have two vectors, the torque vector and the P cross E vector. They have the same magnitude, plus they have the same direction. But that is basically the definition of the vector. A vector is something that has a direction and a magnitude. If two things have the same direction and the same magnitude, they are the same vectors. So this is our torque. The torque vector is P cross E. Now, if there is a torque acting on the system, what is the potential energy corresponding to this torque?
You can say minus of this, because potential energy was the minus of work. So
it's not the minus of that.
Minus of work.
Yeah, it's the minus of work. So what is the work in the case of torque? Well, the work was F dot dl. In this case, torque times t theta. Because what force is in the case of rotation, the torque is the analog, and the analog of the displacement is the same as the change in the angle. So the potential energy minus the torque will be Pe sine theta times d theta. Well, theta is equal to 0. Well, this is from theta is equal to 0 to some final theta, let's say, plus the potential energy at theta is equal to 0. Well, here let me put a minus. This minus is due to the definition of the potential energy. As your friend pointed out, the potential energy is minus the work done. This minus is due to the fact that the torque is in the direction of smaller theta. Torque tries to make the theta negative. So that's why we have this additional minus sign. In a sense, it is like having the force and dl pointing in opposite directions. So this is equal to minus Pe times cosine theta. Theta from 0 to up to final theta t plus u of theta is equal to 0. So u is equal to minus P times E times cosine theta plus Pe cosine 0 is 1 plus u of theta is equal to 0. So u, the potential energy is minus P dot E. I just chose these two terms to cancel each other. It's just a shift. So this is the potential energy of a dipole in an electric field. So if you would plot it as a function of theta, at theta is equal to 0, it is minimum. At theta is equal to pi, it's a maximum. This is theta is equal to 0. Here you have theta is equal to pi. So the system will always try to go to the minimum, which is theta is equal to 0. So if you have a water molecule, we said this is slightly positive, this is slightly negative. What will be the direction of the dipole moment of this water molecule? Which direction will it be? Well, you see, this system doesn't really have just one positive, one negative. In a sense, it has 2 positive points and 1 negative point, but double the charge. So you can just imagine this as, model this, let's say, a positive charge over here, a negative charge over there, plus a positive charge over here and a negative charge over here. So we have one dipole pointing in this direction, another dipole pointing in this direction. So this is one dipole. Then you have this dipole. The total dipole moment of the system will be just the sum of them. So this will be the total dipole moment vector. This is the electric dipole moment of the water molecule. If you put it in an electric field, it will try to align this electric dipole moment with the electric field. So you will be rotating the molecule. Any questions before you go? Okay, see you on Monday.